What's the matter, Allie? Allie. What's wrong, Allie?
How you doing, Professor?
All right, how's it going, Aaron? I just sent out an email to everybody. I got the practice final posted. I might make another one if I end up cutting out those chapters just to uh keep it easier on you. But I had told you what to do in the event that we do cut out those, either the last chapter, which I said was going to be 28, or the next to the last chapter, which I said was going to be 27. If I cut out one or both of those, you just avoid doing those questions. So, but like I said, I might actually later make another one that doesn't have those questions in it at all if I decide to cut out those chapters. It all depends on what I'm able to get done today and next time. So,
I did see a notification for the email, but I am still not home yet. I will be home in maybe 30 minutes, but I'm
okay.
listening.
Yeah, no problem. Just drive safely, and yeah, I'd rather you not pay attention and catch the video later than getting
Nah,
a
physics is more important than driving that.
Now I have been known to make that calculation, and it's not it's made me a very bad driver. My wife and my kids all think I'm an awful driver.
Don't worry, I can multitask. No, I'm just kidding. I'm kidding. I'm kidding.
Yeah, I like to do long division when I'm driving. I'm constantly running my, average speed, my average miles per gallon, and all that stuff. And I keep it in my head, and I like have one time for where I cut out the actual breaks. When we stop for bathroom breaks or whatever. And then the other time is when we're actual travel time. It's pretty fun, but like I said, I'm not that good of a driver because I'm not doing the stuff I'm supposed to.
Speaking of driving, I know it's a little off topic, but you go to campus on Mondays and Wednesdays as well, or
Yes, I go Monday. Actually, I go Monday through
ah,
Thursday.
to the Virginia Beach one, right?
Yep.
I see.
Did you see
I
me?
heard from Nora you drive a truck.
I have a couple trucks, but I actually drive a red Honda Civic.
Ah, okay. Oh, a couple.
Yeah, it's a Deadpool theme. It's
It's
kind
a
of,
what?
but it's good on gas. I was saying it's a Deadpool theme. It's like red and black, so I bought red
Oh,
seat covers and, well, it used to be a red and black front driver's plate with the Deadpool logo, but the bugs have beaten it, so I got another one. I have to replace it. Where are you at? You live in Norfolk or Virginia Beach or what?
I'm I'm Norfolk, or excuse me, I'm Virginia Beach, but I'm like at the border of Virginia Beach and Norfolk. Military Highway.
Yeah,
Yeah, I'm there.
gotcha. Yeah, but no, actually, Military Highway is really long, but yeah, I know that area. That's where I bought my truck. There's like this dude that runs an Italian restaurant on Military Circle, and he was selling this old Dodge Ram, and I went and bought it from there, and then I
Is it?
discovered he lied to me a lot.
He lied to you a lot?
Yeah, which is one of those
Oh boy,
typical used cars sort of deals. Like the engine had
car
been
salesman.
from a junk car that had paint all over it and stuff. And he said there hadn't been any wrecks, and my Carfax came back saying, "No, it's been 3 wrecks."
That was a lie.
That was kind of funny.
Gosh, I don't know what I'm gonna do when I like buy my first car by myself.
Can you guys hear me by any
I
chance?
I can't. We're just
Is
ignoring you.
that
Okay,
Nora?
I cannot hear anything going on. I can just read your lips.
Oh, really?
Yeah, we're just ignoring. Is that Nora?
Let me see if
It
I
is
can
Nora.
leave and then I'll join back in.
Yeah, try that, and also turn your volume on. Make sure you don't have a Bluetooth device nearby. I've been noticing that lately. I'm sitting there on my phone and like I can't get any sound, and I realize my wife's got like my Beats near me or another set of headphones, and mine just picks up better than hers. Oh my god.
I'm kind of having that issue right now because it's like it's connecting to my AirPods and it's connecting to the car, and I'm just like, dude.
That's a pain.
I I did not know our last lab is on Wednesday. I thought it was Monday because I mean last day of school was like August 2nd.
All right.
That threw me off guard.
Yeah, I think
So
Kevin might be doing a
after
little bit more
Wednesday,
with his labs than I normally do. So yeah, you might actually have another day.
really? Okay.
Did you have a
I
day today?
sorry.
Did you have a lab today?
Yeah, we had a lab today. We were working on like our DC motor.
Gotcha.
Oh, you know what? Is how many people's in the classroom right now? I can't see.
Right now,
Is everyone
5.
here? Oh, okay, cool. Um, I guess I must have gotten like some announcements mixed up, but
Mhm.
did you say the final it was supposed to originally be in the lab, but then you decided to consider doing online, or is it like now online for sure?
As long as Kevin can make it, I was still planning on doing it on face to face during lab time, but I haven't talked to Kevin about that yet, so I'll know more probably tomorrow. I'll talk
Okay.
to him tomorrow.
And if it's face to face, it's like still on the 31st. Is it still like
Yes.
10 a.m.?
It doesn't have to be. I'm going to leave that up to Kevin. If Kevin's actually doing the lab, I'll just let it hold during that lab. If not, I can either have y'all meet me over at the Virginia Beach campus, or I can do it and drive to the Chesapeake campus possibly, but I've already got a exam that day, and that might cause some problems. So let's see. But
Okay.
if so, it would probably be if he can't, and he might not, he might have to travel or something. If that's the case, I might get you guys to come over here, or I just might set it up where y'all can take it online with the respond this lockdown browser and everything.
Okay. So it's still like TBD right now, right?
Yeah, it's definitely Monday.
Okay, gotcha.
My intent was to make it 2:30, which I think that's your exam time, and that's what I sent in that email. But like I said, I'll know tomorrow, and everything will be decided by Thursday, or excuse me, by Wednesday.
Cool. Thank you.
Uh-oh. This is not good. I am watching my neighbors drive out their driveway, and neither one of them has a driver's license. Both are blind, and they're getting ready to run over some concrete structure that separates their driveway from the ditch. This is not good. The good news is it's taken them over 8 minutes to get where they are, so I'm thinking they're being careful. Oh, good Lord. Oh, good Lord. Oh, I just found one of them's watching the other one. They're doing like this down the driveway. The driveway's like 50 feet long. There's no swerving.
Rich people.
Getting old really sucks. I feel so bad for people. Luckily, I'm not. I've got this whole plan that I ain't quite worked out, but I'm not planning on getting old or dying or any of that kind of stuff. So I just got some details I got to shake out. Sort of like Joey on Friends, and when he found his hand twin, he was going to be rich. just had to work out the details of how you're going to do it, but evidently. Now Nora came and left again, so she must still not be getting sound. Ruh-roh. All right, well, it's time to start class. I don't want to lose any more time. I'm kind of bummed out about the number of chapters I get to cover with you guys, just because I don't want to shortchange you. But anyways, we're starting into chapter 26, which is basically where we do DC circuits. And then I'm sort of selectively choosing parts of 27 and 28. 27 is just about magnetism, and 28 is about calculating sources or calculating the magnetic field due to the sources of the magnetic field. But I'm just like taking and showing you the main thing that you have to do for those two chapters. So that's why I think I can fit them in. And I would still like you to have 29 and 30, and 31 for that matter, but I just can't do that. And it might even be pushing too much to do 27 and 28. If in fact, I need you guys to, give it your best shot. But if I look and it looks like I pushed too hard, don't worry. I'm a compassionate person. I can tell when I look at a large fraction of the class not getting something. I can tell what part's my fault versus what's your fault. So I will definitely take that into consideration. I don't want you guys stressing out about me testing you on a bunch of hard stuff that you haven't had enough time with. So I will keep that in mind. And of course, y'all can always talk to me. I know y'all send me text messages and or emails and all that good stuff. Oh, someone came back. Nope, it's not Nora. All right, we're up to 6 people in the class now. Hopefully Nora will come back. So what we want to start off with is I already talked to you about how to make a battery. I'm not going to go over all the big concepts so much. You can get that from the reading. But in chapter 26, we start off with batteries, and the batteries are real. So the battery will have a voltage for the ideal battery that will be called the EMF. And they use a script E, so you don't confuse it with the V that's used for the units of volts, or for the V that's velocity, or for the V that's sometimes used for potential energy or various other things, which is, why we in physics are now using not only the English alphabet, but we even have, I got a little Hebrew, we got Aleph null, which I'm sure I'm not pronouncing correctly, but Aleph null is one of the mathematical symbols we use, which literally means the first letter of the Hebrew alphabet with a subscript 0 on the bottom. I think it's Aleph or Aleph or something. I don't know. But we got that. We got symbols we're using from all sorts of languages. So it's kind of a pain. But anyways, with that in mind, they'll have an ideal battery that has an EMF. And then in series with it will be a small resistance that, at least in our model, grows over time. And that small resistance is called the internal resistance. Good deal, Nora. It's called the internal resistance of the battery, and that's how we model it, because it acts like that. Basically, you get to a point where the dissimilar metals that are inside the battery just can't accept any more charges coming back in, and therefore can't really get rid of any charges going out, and it just acts like it's what used to be a 1.7 volt battery with nothing attached to it now is like a 1.49 or 1.45 volt battery with nothing attached to it, when you really need a 1.5 terminal voltage. So that's another term we're going to use, is V terminal or terminal voltage. And that literally means when you connect, it usually means when it's connected, because it's not much use to have a different term for the battery voltage when it's connected versus when it's not connected. But basically, if you just connect the battery when it's not drawing any current except for whatever the multimeter requires, so you're just taking a battery and you're taking the common port and putting it to the negative side, and then on the nipple on the top of the AA, AAA, or whatever battery, you're putting the red V omega sign on it. You've got it on volts. When you read that, that is technically a terminal voltage, but we usually don't use that phrase unless there's a current being drawn from it, in which case it's just that's sort of the ideal voltage. And when you do that with a brand new battery, like a AA, AAA, a C, or a D battery, they'll normally read like 1.72, something like that, which they're nominally supposed to be 1.5. Now, once you connect that battery by running a wire, say from the positive terminal into a light bulb, say out of the light bulb and back into the negative terminal, then it's actually drawing a current, and you check the voltage across the positive and negative. That's the terminal voltage, and it really is extending from the negative side of the battery across the internal resistance to the other side of the battery. So it all depends on where you put the internal resistance. Do you put it on the negative side of the battery, or you put it on the positive side of the battery? The main thing is you want it to include both the battery and the internal resistance and read the voltage difference across the ends. So with that in mind, let me work an example for you. So I'm going to start by sharing the screen, and go ahead and ask me any questions if you have any as we go. Like I said, I'm just trying to sort of hurry through to get you to a place where I feel better about letting you guys go, where you've at least seen like Ampere's law, the god-awful law of Biot-Savart, F equals Bill, which, you know, obviously has a certain ring to someone named Billy like me. So anyways, here we go. I'm going to do share screen now. And now it'll take approximately 38 minutes for the computer system to acknowledge I did what I was supposed to. So just wait for your 38 minutes. Fine. Okay. So this is what we have here is supposed to be a battery. So, and this is the battery according to the model I was telling you about. So what we can sort of picture is this would be, if this is like a AA battery, this would be the positive side. And then of course you'd have the top of the battery, which looks like this. And then over here would be the negative side of the battery, like so. And when I say the terminal voltage, what I mean by that is actually the voltage. So let's imagine a little voltmeter here. I'll say this knob is set to volts and it's got a straight line over it. So that means it's DC voltage. And you've got a COM port. And that is connected to this side. And you've got a V omega port, which the V is the relevant part. So I'll write that right here. And then you connect that to this side. Okay. So this is V terminal. And that's what we mean by it, because it actually has a load on it. And with that load, that means it's actually having the current make the voltage drop so that we can actually get a realistic figure for what the voltage is, at least when it's under load, which is what the more important parameter is. You know, we don't need to know how much voltage the battery has when it's not connected. We really need to know when it's connected, what's the battery got. So here's the V term that I was saying. It wasn't obvious that I wrote term there. So that's what I mean by V term. So this problem basically gives us a 9-volt battery. That's the ideal battery. And in fact, the symbol for that would be the script F, which means EMF, which is electromotive force. Your book makes a point to make sure you know it's not actually a force. It's not measured in newtons. It's just another voltage, but they originally when we came up with it, they figured there was some way that the electric type things are getting a motivation to move, and hence they call it an electromotive force. So that's just where it ends up. We still use the phrase. We usually just use EMF. That way it doesn't, if you don't break it down, it don't sound like a force. So what we're going to do is in part A, they want us to calculate the total current. And in part B, they want us to calculate the terminal voltage. And then in part C, they want us to calculate the power dissipated by the internal resistance compared to the power dissipated by the resistance R, which is the load. Okay. So I think from your experience in lab that if you took the voltage across the 0.5 ohm resistor, and then you added to that the voltage across the 70 ohm resistor, you would know that that total voltage is actually equal to the voltage of the battery. And that's what we're going to use using Ohm's law, where we say V equals IR. Then what we're going to do is we're going to say 9.00 volts is equal to I times 0.50 ohms plus I times 70.0 ohms. Obviously, that allows us to combine like terms. So I'll get 9.00 volts is equal to 70.50 omega times I. Okay. And this is all part A, by the way. So I can clearly find I by dividing the 9 volts by the 70.50 ohms. And I underline that 0. So if you're wondering what the symbol is, it's just me underlining it, showing it's not a real sig fig. So I'm going to do 9 divided by 70.5. And that gives me 0.1277. That's one extra sig fig as well, amps. So that's also about 128 milliamps. That's the norm when you're using ohmic style resistors and basically 1 and 2 digit voltages. You're often going to get milliamps, that sort of thing. So that's the answer to part 1. Now I did a little hand waving there. You'll notice in the next section, because I'm going to tell you what you've already learned about how to deal with resistors in series and parallel. That happened to be me just dodging that by realizing that you knew that the voltage drop across each of them add to give you the total voltage drop. So I basically skirted that fact by doing it. So now part B, they want to know what's the terminal voltage. So the terminal voltage, if you can use the idea of the little bubbles I talked to you guys about before, you could say this is going to be ground, and you could just write it like this. Now, it doesn't have to be ground, but generally speaking, if there's only one battery in the circuit, you might as well put the ground at the negative side of the battery. And that's what we did. Now, if you take and connect the COM port to this spot and then the V to various other spots, you'll get these little bubbles that I like to use. This one's 0 volts. This one right here would be 9 volts because we're just across the ideal battery at that point. But then when you get over to here, that's going to be the V terminal that we want. So really all I need to do to figure out what V terminal is I know that V right there at that positive side of the battery is 9 volts. And then I know it's going to drop IR and going across that little resistor, lowercase r. So I'm going to say V terminal is equal to is equal to 9.00 volts minus 0.1277 amps times 0.50 omega. Okay. So obviously this is 9.00 volts. and then 0.5 times 0.1277 should be 0.06, and then 7 would be 3.5, and then this would be 8, and this would be a 5 here, like that. And that's, of course, way too many sig figs by 2, and that would be volts as well. So if I take the 9 volts, I'm double checking my math here, 0.06829 is what it got. So that was, yeah, I got a 8.5, but anyways, I'm going to subtract that from 9, and that's going to be about 8.93. Now notice there's only 2 sig figs that we should have, because the 9 volts only to 2 decimal places. So I shouldn't say sig figs. We should have 3 sig figs, but we're only going to have 2 decimal places. I'll put an extra one here. That's a 6, and that's just good practice. Remember, you always want to keep one extra digit of sig fig of non-sig figs, just so you can use that for subsequent calculations. But you also want to keep track of it. So the way I do it is I tend to underline them. So this is the terminal voltage. That was another thing they asked for in part B specifically. So that's V terminal. So we got part B. Now part C is PR equals question mark and P big R equals question mark. So what we know is P is equal to IV. So if we know the I and the V, that would be good. But we also know V equals IR. So we could say I squared R. And that works well as well. So I'm going to use that one just because we already calculated the I. And the I is pretty straightforward calculation. It's obvious that both the lowercase r and the uppercase r have the same current. So I'm going to say P sub little r is equal to 0.1277 amps squared times 0.50 ohms. So 0.1277 squared times 0.5 gives me 0.008. Now notice that's the first sig fig technically, and we only have 2 sig figs to work with due to the multiplication. So I'm going to call this 8.1. And in fact, the next digit is a 5, but it's always questionable as to whether it was a 4 that rounded to 5. So I always put 2 digits when the next digit is a 5. So I'll put 5.3. And that's the power in watts. So we call that basically 8.2 milliwatts. And only the 5 and 3 are actually underlined there, but it's not obvious the way I wrote it. So let me see if I can do a little better. Okay. Close enough. Okay. So 8.1 milliwatts is basically the power dissipated by the little internal resistance. You can actually feel, again, it's not really technically a separate resistor inside of the battery, but there is something just like it. But you can feel that a battery actually gets hot when it's being used. I don't know if you've noticed that with your cell phone, but I definitely notice my cell phone, the more I use it, the more it'll get hot. And then also sometimes when you're charging it, you can see it as well. Now we'll calculate the big R power. So power through the load is going to be, again, 0.1277 amps squared. Now this time the resistance is 70.0 ohms. So that gives us 3 sig figs. So 0.1277 squared times 70 gives me 1.14. And the next digit is a 2. So that's 1.14 watts for that one. Any questions on that? Okay, and those are things you just can't get away from. You're going to waste power whenever you run current through a load, and that power is given by IV I squared R V squared over R. I think that might be the other one. But anyways, the main thing is you can calculate it using P equals IV and then use Ohm's law V equals IR. So for instance, if I wanted to eliminate the I, that would have been V over R. So yeah, that would have been V squared over R. So yes, that's another form. Okay. All right, now that we've done that, I will choose to take a second and just remind you that if you have, for instance, a battery in series, say, with resistors like this. Now I'm gonna make the battery really big because of my line. That's going to be R1, R2, R3. And you can look at my YouTube channel to see derivations, or you can look in the book. The big thing is, you know that the sum of the voltages is equal to the total voltage. And the total voltage is I times the total or the equivalent resistance. But also the individual voltages are I times R1, I times R2, and I times R3. And I1 equals I2 equals I3. So you end up getting just R equivalent in series is just R1 plus R2 plus ... for however many resistors you have in series. Similarly, if you have, let's say, a battery here and a resistor there, and then another resistor in parallel with it, and another resistor in parallel with that. So this would be R1, R2, R3. Someone else just came in. Oh, hell on. Okay. Well, in this case, we got that, but in this case right here, we're going to get 1 over R equivalent parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus ... Okay, so the reciprocals add to give you the reciprocal of the whole thing, and these are the worst looking R's I've ever seen in my life. So that's another key point. Notice that is exactly the opposite of the formula we found for capacitors. Capacitors, we found that when they're in series, their reciprocals add to give the reciprocal of the equivalent capacitance. And in this case, it's the other way around. The main thing to remember about this is this formula mathematically says that the equivalent resistance of all of them will be less than the smallest resistance in it. So if you have a 3 ohm resistor, a 100 ohm resistor, and a 1,000,000 ohm resistor, and you put them in parallel, the total resistance will be less than 3 ohms. If you put them in series, obviously, they will be greater than any of them, greater than the largest ones, another way of saying it. So that's something that comes in handy. For instance, if you ever need to make a circuit and you need a specific resistance, say a 1 ohm resistor, it's very hard to find a 1 ohm resistor for starters. But what you can do is you could take 10 ohm resistors and put them in parallel. And then you get 1/10 plus 1/10 plus 1/10 10 times. That ends up 10 over 10. So 10 over 10 is just 1. And that gives you equivalent resistance of 1 ohm. So that's partly what that's about. Now that we have this formula, I want to go ahead and show you a very typical type of example you should be able to solve. Let's look at, for instance, this guy right here. So I'm going to draw a circuit. I'll put the battery right here. I'll put a wire right here. Put a wire here. Wire here. And that's one resistor, which was looking really good. And then the auto thing just made it look like crap. Now that's going to break apart into a parallel system. That parallel system is going to have 2 resistors. and then they're going to come back together and go back into the battery, which will have that little part right there. I'm going to say this battery is 12. Well, let's stop doing the auto fix thing. This battery is 12.0 volts. I'm going to say that this is 300 ohms. This one's going to be 400 ohms, and this one's going to be 500 ohms. Notice when I have a resistor drawing, if I actually put the ohm on it, that's redundant. So I really don't have to do that. The symbol does that. So we often use that quickly. It's not necessarily the best practice, but it's a time saver. So what we want to find is A, R equivalent equals question mark. And then I'm going to go farther and say B, what is V 300, V 400, and V 500. So that's what I'm going to do. I'm going to say solution. And the first thing I'm going to do is I'm going to choose any two resistors that you can simplify. That's the way you do this when you attack a nest of resistors in various arrangements, is you look for any pairs or 3 or 4, any more than 2 or more that are arranged in a very simple form, either all in series or all in parallel, and then you can reduce that to 1. So I'm going to say that this circuit is equivalent to basically the same 300 ohm resistor followed by what I call as R equivalent 1. Okay. Now, what is that? Well, that is 1 over R equivalent 1 is equal to 1 over 400 plus 1 over 500. Now, I happen to know that 400 does not go into 500. And in fact, 2 times 500 is 1,000, 3 times 500 is 1,500, and 4 times 500 is 2,000. 400 does go into that. So that's our least common denominator. To get that, I have to multiply 400 by 5. So this is going to be 5 over 2,000 plus, to get that, I have to multiply 500 times 4. So this is going to be 4 over 2,000. And that ultimately gives me 9 over 2,000. And therefore, R equivalent 1 is actually 2,000 divided by 9. Well, that's not the easiest thing, but normally I'd like to do the arithmetic and work that out, but I'm just going to quickly divide it by 9 using my calculator, and that gives me 18. Whoa, no. Oh, no wonder. 2,000 divided by, I hit multiply, and I was like, how did I get 18,000? That's 250 is equal to 250 ohms. So now this is 250 ohms. And then I can say this is equivalent to 1 resistor of 550 ohms in series with a 12-volt battery. Okay, so that's what the equivalent is. And the reason why that's helpful is it allows you to also start working on what the actual voltages is, because because the battery doesn't know necessarily what's going on the other side. In fact, it's almost like the battery's like got a magic sense of consciousness, and it knows the equivalent resistance, but that's all it knows. So far as the 12-volt resistor is concerned, 12-volt battery is concerned, it thinks it's just a 550 ohm resistor in series with it, and it sends out current accordingly. So there's going to be a little bit of current I going across here. I've already figured out that R equivalent is in fact not that one. I've already figured out that R equivalent is equal to 550 ohms. So I'll go ahead and circle that. And that was part A. Now for part B, I'm going to go ahead and start computing things like V500, V300, V400. In other words, what's the voltage across there? In order to do that, I need to know the current, for instance, going through the 300 ohm resistor. The current going through the 300 ohm resistor, if you multiply that by 300 ohms, that's going to give you the voltage across it. And that's true for any resistor that's only separated from the battery by another resistor or just wire. So if I had a resistor after that 400 and 500 on that right leg, that one would also have the exact same current going through it. So what we're going to do is we're going to say 12 point, using Ohm's law, 12.0 volts is equal to I times 550 ohms. Okay, again, that's all the battery knows about. So it thinks that's the whole current there. So that's how much current is sent out. Well, you don't have any junctions between the positive terminal of the battery and the 300 ohm resistor. So all of that current has to go right through the 300 ohm resistor. And when we do that, we get I. All of a sudden I'm yawning. Haven't yawned at all the whole day. I get I, which is 12 divided by 550. That's obviously going to give us something on the order of milliamps, and I get 21.81 or 0.02181 amps, which equals 21.81 milliamps. Okay. Now I'm assuming we had 3 sig figs there with the 550, which isn't necessarily a good assumption. But it depends on whether the 300, 400, and 500 had 3 sig figs. So we'll just take it like that. Now I know the total current going through there. And in fact, I can use this because remember, this is the current going through the real circuit as well. So I can say this part right here is 21.81 milliamps. And if I use my bubbles, of course, this is 0 volts. This is 12 volts. Right here is 12 volts as well, right? Because the resistances of the wire are much smaller than hundreds of ohms. So you would find that it's actually less than 12, but it might be 11.999. So your voltmeter couldn't even tell. But I can figure out what this is because I know it's 12 volts there. And if I subtract from it I times 300, that will be the voltage drop across the 300 ohm resistor. So I'm now going to go ahead and take and say V, I would probably want to stick with the same color. V300 is actually equal to 0.02181. That's technically 2182. And I'll change that here like this. Just because I didn't round it, it's 18181818. So obviously it should have been 2. So 2182 amps times 300 ohms. Whoa, that's some crazy stuff just happened. Like that. And that gives me V300 is 6.5454. Volts. So the voltage across the 300 ohm resistor is 6.54 volts. Now that means if we take 12 from if we take that from 12, which I'm going to do the opposite way and just erase the negative, I get 5.45. So I'm going to say this is 5.4545 volts right here at this bubble. Notice that also has to be the case at this bubble and at this bubble because there's nothing but a wire connecting the right edge of the 300 ohm resistor and the left edges of the 400 and 500 ohm resistors. Does that make sense to everyone? Now, if we look back, the 0 volts is at the negative side of the battery, but that also means it is here and it is here. So we already know what the voltage is across the 400 ohm resistor. It's 5.45. But I'm going to go ahead and calculate it to make sure you guys agree. So I'm going to write here that V400 equals V500 is equal to 5.45. Now notice that next number is 4, but if I rounded it, it would become 5, and I'd be in that predicament again. That's why I wrote 4.5 again. So that's what the actual voltage is across those. But let's assume you didn't do that. What we do know is, well, let's ask you, how are the 400 and 500 ohm resistors connected? Are they in a special way, like series or parallel or anything like that? Nora?
I knew it. The 400, 500
Uh-huh.
parallel.
Yeah, they're in parallel because really you've got two paths for that current where it breaks out of the 300. You've got a top one, which is only the 400 ohm, and a bottom one, which is only the 500 ohm. So yeah, they're absolutely in parallel. So that means V400, actually, let me write it in blue. So V400 equals V500 because 400 ohms and 500 ohms are parallel. Okay. Now we also know from Ohm's law that V equals IR. So I know that I 400 times 400 ohms is equal to I 500 times 500 ohms. So that's the equivalent of this. Okay. But if, let's say, 100 charges came out of the 300 ohm resistor and 75 of them went to the 400, how many would have to go to the 500? It was 100 total and 75 went to the 400. So
The rest of the 100, so 25.
yeah, 25. So that's a key thing to understand. And that's actually going to be called Kirchhoff's junction rule. So yeah, thanks, John, for that too. So what that means is we've got another equation that says I is equal to I 400 plus I 500. And I, of course, we knew was 0 0.00, or excuse me, 0.02182 amps. Okay. Now, if I look at, let's say, let's call this equation 1, let's call this equation 2, I can say that, for instance, I 400 from equation 1, I 400 is equal to 500 over 400 ohms and ohms times I 500. Well, 5 over 4 is just that, 5/4 I 500. So now I can plug that into equation 2 to get 5 over 4 I 500 plus I 500 is equal to 0.02182 amps. So 5/4 plus 4/4 is 9/4. So I'm going to say 9/4 I 500 is equal to 0.02182 amps. So now I can say that I 500 is equal to 0.0 0.02182. And now I'm going to take that and multiply by 4. And then I'm going to divide it by 9. And that gives me 0.0099698 amps. And then, of course, I-400 is equal to 5/4 of I-500. So that's 5/4 times 0.009698 amps. So times 5 divided by 4 gives me 0.01212 amps. Okay. And if you add those two, you can see that they do in fact give you 0.02182 roughly. Okay. Now that we have that, we can now figure out what I-400 or what V400 is. So V400 is equal to I-400 times 400 ohms, which equals the I-400 is 0.01212 amps times 400 ohms. And you get 4.84. Oh, Nelly. I did say right. I did do 5, I did do 4. 400 is a bigger. Something weird is happening. Let me check my math again real quick. We said 0.02182 times 300. That gave me 6.456. Now I subtract that from 12. That gives me 5.454. So that's what it should be. But for some reason, I'm getting 6.546. Oh, no wonder. Oh, wait a second. No, that's not right either. So my current 0.01212 times 400 is equal to, now it gave me something entirely different. Good Lord. I don't know what's going on here. I just got 4.8 that time. And I got 6.5 the last time. Anybody, please help me here. Let's check my math real quick. I did say the total current I was 0.02182. So equation 2 looks right. I-400 times 400 is equal to I-500 times 500. That's right. When I solve for I-400, I should get 500 over 400. So that's right. That does reduce to 5/4. So I put 5/4 400 or I-500 plus 500. And 4/4 plus 5/4 should give me 9/4. So that's right. Let's check my math on 0.02182 times 4. And now I'm going to divide it by 9. 0.096977777, which is basically 8. So that checks for me. So I've now checked that. I've checked this equation. I've checked this equation. And I've checked this equation. So that's the I-500. And then the I-400 should be 5/4 times that. So I'm going to say times 5 divided by 4. That gives me 0.1212. 0.01212. So that checks. Now if I multiply that by 400, now I got 4.84. Bless you. So I'm getting 4.849. volts. Now I'll check V500, which again is just the I500 times 500. Now the I500 we found was 0.009698 times 500. And that gives me 4.8492 or as well. So these two are definitely supposed to be correct. This is V400. Now, I don't know why. I'm getting ready to try to figure that out. I don't know why we didn't get the same thing as when I did my bubbles, so I got to double check my work here. We did find that the total resistance was 300 plus 250. That should be 550. So if I take 12 and divide it by 550, I get 0.02182. 02182. So that checks as well. Okay, and now if I multiply that by 300 times 300, that gives me 6.5454. And now if I subtract that from 12, let's check that at 6.5454. So this number checks as well. So I'll say minus 12. That's supposed to be the voltage of the battery. I got 5.4545. Still can't figure out why that's not 4.84. Did I use the proper current for the total current? I400 plus I500 has to be 0.02182. Yeah, that works too. So I did that correctly. Anybody see anything that I possibly did wrong?
Professor,
Uh-huh.
when I do the resistance for equation or the resistance one,
Uh-huh.
2000 divided by 9, I get 222.2.
Okay. Where did that 2000 come from too? I remember finding out about that 2000. Oh,
Yeah.
gotcha.
Says
Yeah.
the invert, yeah.
So yeah, maybe that's the problem. So 9 divided by 2000, and then we flip it over. Just checking, just make sure. Oh, so you got 222. That's what it is. Okay, so
Yeah.
that's what went wrong. Thank you very much for that. So everybody, I'm going to leave this like this and say no. And it's actually, I don't know what. Oh, I bet you I typed it by 8 or something. That sounds like what I did. I typed 8 instead of a 9. So it's actually supposed to be 222.2 ohms. So that's the R equivalent, and that means this is wrong as well. So I'll say no. And this is now going to be 520 ohms. So that makes everything different. So now I'm going to replace this with 520. I'm going to replace this with 520. I'm going to replace this with 222. Oop, nope. 222, not 520. So that's 322. So don't replace it with 520. I want to replace it with 522. Well, let's not change colors midstream either. And this one is going to be 22.2. Because the 300 plus the 222 still gives me 500, but it's 522.2 now. And this one also was a boo-boo. Man, I made a boo-boo after a boo-boo. So 2.2. So that looks like everything's cool there. That means this is no. And what I'm going to do is say 12 divided by 522.2. And that gives me 0.0222298. Zero point zero two two nine eight amps, which equals 22.98 milliamps. So this part is actually correct now. So now I have to do is replace this 0.02298 amps. Zero point zero two two nine eight amps. Got that. So 0.02298 amps again. This gives, so now what we're doing is we're taking the 0.02298 amps, and we're multiplying it by 4 and dividing it by 9, and that gives me 0.0102. So now that we got all these, what I'm going to do is leave that there, and I'm going to take it from here and say I500 is equal to 0.0102, and then the next digit is 1 followed by 3, so that's amps right there. And then I'm going to replace, that's the 500, so I'm going to replace that 009 with parentheses 0.01021 amps. And that's times 4. So I'll say times 5 divided by 4. That gives me 0.01277. 0.01277 amps. So that's the new current. And I can replace the I400, which we found was that amount. I'm going to replace that with 0.01277 amps times 400. And this better give the 5 point something other that we got. So now I'm going to say 400 times all that number. And that gives me 5.10. Zero. That's 3 sig figs. The next one's a 6, but it's followed by a 7. So I'm going to write 7. And that's volts, and that's V 400. And I can also change V 500, which should be 0.01021 times 500. That gives me 5.105. That's like that. And now let's check our bubble calculation since that wasn't right either. Nor was the 2181. Dang, that's a nightmare. So yeah, this is now that I'm correcting it, let's see. The current is supposed to be 12 divided by 222.2 or 522.2. So 12 divided by 522.2, that gives me 0.02298, which I had somewhere written, but oh, there it is. Yeah. So this becomes 22.98 milliamps. That's what's going through there. Now that also means this 5.545 is not right, which I can change. And what it's going to be, put that back up there, is it's going to be this 0.02292 times 30 or times 300. That gives me 6.89, which I subtract from 12. And that gives me 5.107. 10, actually it's 1060, so I should write that as 106 volts is right here. Okay, so in that case, we would make the I would have made the prediction that that's supposed to be the voltage across these two, and we would have been actually right this time because, you know, I used the right number, so that's kind of helpful. 106 volts. So again, you can still use the bubbles. The bubble did come to 5.106 at the end of 300, which is also supposed to be the voltage at the left side of 400 and the left side of 500, and then the right side of 400 and 500, 0. So we did, in fact, get exactly the same voltage, at least to the sig figs. In all cases, to 2 decimal places, which is 3 sig figs, it should have been 5.11. And that's what I got for V400. That's what I got for V500. And that's what I got for both of them using the bubble method. And I'm just saying it's a bubble, but it's really just a, just a circle like I'm reading the voltmeter. Anybody, everybody follow that? I know that was a nightmare after I made that one little error and had to go back and correct it. But let me recap and say what I did. So the first thing we did is we reduced the 400 and 500 ohm resistor to R equivalent 1. That was 1 over 400 plus 1 over 500 equals 1 over R equivalent 1, which you see next to the A. The common denominator was 2000, so I multiplied the 400 by 5 over 5, which gave me 5 over 2000, and then I multiplied the 1 over 500 by 4 over 4. That gave me 4 over 2000, and 4 over 2000 plus 5 over 2000 gave me 9 over 2000. And then once I properly divided 200 by 9 and did not get 250, I got 222.2, which I really can't believe I even thought for a second that 250 was right. But anyways, that's what the equivalent resistance of those two are. Then all I had left was that 222.2 ohm resistance in series with the 300 ohm resistor. So that made it 522.2 ohms is the equivalent resistance of the whole thing. Using the fact that the voltage of the battery is equal to the current leaving the battery times the equivalent resistance, I had 12 equals I times 522.2, like that. And that gave me the 0.02298 amps. Once I had that, I could then calculate, since the current leaving the battery has to go through the 300 ohm resistor in its entirety, then I know that the voltage drop across the 300 ohm resistor is just 0.02298 times 300. When I did that, I should have gotten, so this is another part that I got to correct. Let's fix this real quick. So 0.02298 amps times 300. That gives me 6.89, which is obviously slightly different from this one. So this is 6.894 volts. So that's the new correct number. Now, once I had that, I can do 12 minus 6.49, which I'm actually going to put over here so y'all can see where it came from. So I'll put this arrow here. And I'll say this is 12.0 volts minus 6.894 volts. And I get 5.106 volts. Okay, so that's where that came from. Now, what I said was, again, because there's only wire between that bubble spot and the left of the 400 and that bubble spot and the right left of the 500, then I was making the argument that the voltage on the left end of the 400 and 500 ohm resistors are each 5.106 volts. And since there's nothing but wire separating the negative terminal of the battery and the right side of the 400 and 500 ohm resistors, then those should be 0 volts as well. That gave me the total voltage across the 400 ohm resistor, which is also the same as the total voltage across the 500 ohm resistor because they're in parallel. And I said that was 5.106 volts. That's what I got written here under the word bubble. And then just to convince you guys that it worked, and this is always a good thing to check when you're doing a problem anyways, is look that you can get it and make sure that you can get it in multiple ways. So in this case, I realized the voltages had to be equal. That means IR for the 400 has got to equal IR for the 500. But I also knew that conservation of charge says that if you've got 22.98 milliamps going in, then the sum of the two going out have to be 22.98. So that's how I made equation 2. And I combined equation 1 and 2 to find out I-500 and then I-400. So we've got a lot of extra answers here that weren't requested, but all of them were completely fair to be requested. So for instance, this is I-400. And I did not ask for that. The book didn't ask for that or anything like it, but yet I was able to get that as well as the I-400. Okay. Any questions on that? Hopefully that recap made it a little easier. If you'll notice, this is just like an example that your book did. So I'll say, let's try a different color. I'm going to say C. Whoa, Nelly. I'm going to say C examples 26, 3, and 4. Because basically, if you combine those two examples, that's essentially what we just did, except we had different numbers because we made up a different problem. But either way, it's the same sort of deal. Anybody have any questions on that? Okay, something else your book does, which I really like, is it asks you in the opening questions about connecting two headlights or two lights that are identical to a 12-volt power source. So I'm going to work that out for you real quick. Let's change this back to black. All right. So what I'm going to do is I'm going to picture a battery that's 12 volts. And then I'm going to imagine a cord coming off of it. And in that, I'm going to get a resistor that really represents a flashlight or a headlight. And then another resistor, which represents an identical headlight. So let's say this is R and this is R. And I'll say identical headlights. Now, really what matters as far as how bright a headlight is how much power it's dissipating. That sort, I mean, and of course, if you're comparing one light bulb to an entirely different type of light bulb, then you just can't compare power to power. Because for instance, a compact fluorescent light bulb can be as bright, for instance, as a 120 watt light bulb and only draw 35 watts. So that's not a fair comparison, but these we'll say are incandescent. And what they want to know is what's the best way to connect them. So would we like to put them in series like this, or would we like to put them in parallel like this? In which case we're going to go R and R like that. Okay. So the big question is, which is better? So here's our solution. For series, R equivalent is equal to 2R. Therefore, I is equal to V equals IR. So that'd be 12 point, or let's see, let's just call that V instead of, actually, let's call that, I'm going to call that E. So this is just E over 2R. Okay. And notice also that V1 equals V2, which is the voltage across the first one. And the voltage across the second one. And in fact, by symmetry, since the whole thing has a voltage of E, each one must be a drop of E over 2. So that tells me that P series is equal to IV, gives me P series, this is the total power dissipated now, is equal to I, which is E over 2R, times V, which is E over 2. And this is all for the first light. And then for the second light, I'm going to get the same thing, which is E over 2R times E over 2. So you can see basically I get E squared over 4R plus E squared over 4R would be 2E squared over 4R, which is just E squared over 2R. So that's the total power in series. Now I'm going to do in parallel. So in this case, you can really see how what I told you earlier, that when you put resistors in parallel, the total resistance is less than the smallest one. So what I'm going to find is 1 over R equivalent is equal to 1 over R plus 1 over R, which is 2 over R, which means R equivalent is in fact R over 2. That implies I is equal to E over R over 2, which is in fact 2E. Oh, no, that didn't go well. 2E over R. Now, the other cool thing is that V is just equal to E because they're in parallel. They both have the same voltage, and the voltage is the total voltage of the battery. So all of this means that P parallel, switching to blue, is actually equal to 2E over R times E plus 2E over R times E, which obviously becomes 2E squared over R plus 2E squared over R, which would be 4E squared over R. So 4E squared over R is greater than 1/2 E squared over R, implies parallel is on the order of 8 times brighter. Okay, so it also asks, well, which way do you think you could connect them? Well, obviously, they're going to connect them in parallel because you get the most bang out of it. Not only that, for those of you who are old enough like me, which is literally none of you, but anyways, we used to have Christmas lights that were always in series. And when one bulb went out, the whole light just turned, the whole cord just turned off. And you had to go ahead and basically take each light bulb out until you found the one that, when replaced, made the whole thing light up. So that was a real nightmare. Well, that's what's going to happen if you have the light bulbs set up like they are in the left diagram. If one of them burns out, and that literally means that little hot wire that's got a series of loops in it, that got so hot that the metal melted in two and therefore opened the circuit. So you wouldn't have any way for the current to make it past either R1 or R2. Therefore, neither one would either one would light up. So yes, they are connected in parallel. And light receptacles are connected in parallel. Any questions on that? All right, so that's a typical type of problem you can solve. You can actually solve another problem as well. We're going to do that next, but I'm going to go ahead and give you guys, let's do a 8-minute break. So come back at 6:50. I'm here if you have any questions for me, by the way. I am also going to.
I got into class late, but I was curious if anybody asked about the nature of the final exam.
Yes. Okay. So I just sent out an email about that just before class started. So you should get it in your email. You should have already gotten it in your email, but I sent it through SIS. So it goes only to your TCC email. But that being said, let me pull up my screen and see if it's actually still available. Of course it's not. Let's see if I can get it this way. I'm going to stop sharing for a second, and then I'm going to pull open this, and I'm going to pull open that, and I'm going to try to click on the SIS and see. No, that did not work. All right, let me try another route. Let me see if I can open up my Microsoft. Okay, got that. Ah, here it is. Okay, so I'm going to pull open, actually, I'm going to share my screen now with you guys. Share screen. I'm going to take not that one, this one. Okay, so here's the email I just sent to you, folks. It says, I've made a practice final exam for chapters 17 to 28. The last question is from chapter 28, and the next last question is from chapter 27. If I decide to remove chapter 28 or 27, you can just ignore the relevant questions. I will decide this Wednesday at the end of our class in lab time. Your final exam is at normal lab time. Again, I said I think I got to talk to Kevin about that one. I wasn't sure that your lab time starts at 2:30. I think that's what I remembered. And I was writing it off in my head. But two, I got to make sure Kevin's going to be around. Otherwise, someone else has got to do it, or we got to do it online with Respondus Lockdown Browser. But it's Monday, 7:31, normally at your lab time. I gave you some other times that I'm available to help you guys. Like if y'all have any question and answer session, or if y'all have any questions and we need a Q&A session, I can do that. I also have office hours down here. And I said, finally, I've decided that only the homework and conceptual homework from chapter 17 through 26 are required. Any chapters outside of those would just be counted as extra credit. And then I gave you sort of a reminder of what you're supposed to know how to do for the test. And really, it's these things up to solving a capacitor charge and discharge problems, unless I actually do get to use chapter 27, which will include this one. And if I get to use 28, it'll include this one as well. So I'm not sure that I will, but that's basically what's going on with the test. We'll know everything come Wednesday when we meet for class and see how much we're able to cover. So,
Okay, thank you.
question on that? That cool?
Yep.
I'm going to stop share, and I probably need to remember to erase that because I don't want to put my email address out in the open forums on YouTube. So I'll take that part out. So you guys will just have to get it from there. Anyways, you'll see it from your email. I think all your class accesses your email. I have one student in my face-to-face class that says he doesn't even know how to check his TCC email. So if you've got that problem, you might want to get someone from your class to forward it to you from their email account. Anybody else have any questions? I was wondering why Elron left. Now I've seen his note. I really want to take time to do this next problem in your book, but I don't think I will, because I think I need to get to the more important part, which is how to do it in a reasonable algorithmic way that works every time. So I'm going to do that instead of the next example, which according to your book was supposed to be example 26.7. So I want you guys to check out 26.7. It's basically what I just did with the example with the two resistors in parallel that happen to be in series with another resistor, except this is a more complicated resistor system. So definitely check that out. Or you can look on some of my past videos, because I did that in my YouTube channel. Actually, let me pull up my YouTube channel and see exactly what videos did that. I just went to my YouTube channel and typed in next to the search just as circuit and RC circuit charging, 3 current circuit applying Kirchhoff's laws, LR circuits, solving circuits. Yeah, these all look pretty good. So yeah, if you just do a search for circuit, you'll find plenty of them. And the newer ones are a little better, at least in the fact that I wasn't using paper and pencil. I was using the iPad. But there's a couple of them that is discharging a capacitor and charging a capacitor. Those are important too. I'm just going to give you those equations today and show you more or less how easy it is to use them. But I should probably point out some of these on there as well. So I will do that. All right, it's looking like it's getting close to 7:50 now. And then we got 2 more minutes, and then I'll jump back in on it. You like my shirt? I got it from the Quickie Mart in North Myrtle Beach. Or actually, I think I got it in Myrtle Beach in that case. Who needs a Quickie Mart? I do. All right, it's time to start back up now. All right, everyone. So let me start sharing my screen again. What I'm going to tell you here is a little note. I'll open this. Should pop up in a second. So I'm saying, look at the example, and the example I am referring to is example 26-7. Or look on my YouTube channel for circuit. So I just, like I said, I did a search for the word circuit in my YouTube channel, and let me show you all the things it came up with. And actually, let's do stop share. Let's do different share. Let's do this. Okay, so you look right here and you see circuit. That's all I did is search for. Remember, don't do it up here. That just search the whole internet, and you'll never find my YouTube channel on the internet. I can't find it myself. I just happen to know the address. So, but yeah, if you come down here, that'll do a search for my page. And RC circuit charging, that actually happens to be the very last section of this chapter that we're doing right now, which is chapter 26. Three current circuit applying Kirchhoff's rules. So this is a typical circuit where you're solving a RC circuit to find the three currents in there. Skip this one, but these first two are good, even though they're 3 years old and written with paper and pencil. You can download the actual notes in paper and pencil. You can download them from my from my Google Docs. If you can't find it, let me know. I'll send it to you directly or whatever. Skip this one. Capacitors in a circuit, finding equivalent capacitance. This is the stuff I did 2 chapters ago, so you can skip that one. But solving circuits, charging and discharging capacitors, and making ammeters and voltmeters, that's basically the entirety of chapter 27. So that's probably the single most useful one to use. And you'll notice that was done in February of 22. So that's more recent, and it might have been done with the iPad. Applying Kirchhoff's rules, circuit rules, and charging a capacitor. And then you see down here, Kirchhoff's rules, RC circuits, ammeters, voltmeters. All these are, again, just different different instances of me working those same problems. So if you look at any of these, they're going to help you plenty. You don't have to do the inductance one. That's the next, that's 2 chapters from now. Simplifying resistor configuration, solving circuits, and an extra credit problem. This is one that's really recent. So I know this was done with the iPad instead of the notes, instead of the paper and pencil. So this is a good one as well. So you might want to put those names down for them, or take a screenshot really quickly. But the main thing is, like I said, the Kirchhoff rule example, series and parallel resistor current and voltage. So all these different things are really good. The newer ones, like I said, 5 months and a year are probably better. But definitely check those out. I'm going to stop sharing this now, and I might even put some more links later if I get time. But that's what you need to be able to do, and that'll help you for you missing example 26-7 as I put on here. So now I'm going to go back and share the screen from my iPad, which I know I shouldn't have not done it because I shouldn't have taken it off it because it takes so long, but here we are. All right, so I'm going to go ahead and tell you guys what Kirchhoff's rules are. And this guy, Kirchhoff, actually did a lot. So you'll, if you ever take an astronomy or astrophysics course, you'll learn about Kirchhoff's laws there too. And same guy, but entirely different scenario. And that scenario is talking about how stars can make spectra, which is a very relevant thing to astronomy. But it's the same guy, and that's very common. Brilliant people are brilliant in several areas, and they do really amazing things in several areas. So that's kind of cool. What I'm doing is I'm skipping example 26.7 or anything like it, where you're actually brute force analyzing a series of resistors in series and parallel, finding the equivalent resistance, and then working backwards to find the current through each resistance, and then the voltage across each resistance, and then using the junction rule for the individual currents going into splitting wires or something like that. It's just basically the same thing I did with that last example, but in a much more complicated example. So I'm not going to do that. Like I said, you can look it up and see how your book does it, but you can also look at those videos I just pointed out for you. Those are good too. What I want to do is get into using Kirchhoff's rules, which start basically with example 26.8. So that's where I'm going to go now. Okay. So what is example 26.8? Well, they're going to have this little circuit down here. I'll show it to you. Basically, we're going to have a wire runs into a battery. That battery has a voltage of 80.0 volts. I'm going to pretend like everything has 3 sig figs. It then runs into an internal resistance of 1.00 ohms, and then goes around the bend, goes up here, and runs into a resistance of 20.0 ohms. And this wire goes right back to here, and this wire goes to here. Now here, there's another battery. It's actually oriented in the opposite direction. This one's 45.0 volts. And now it runs into a internal resistance, which is 1.00 ohms. And then it runs into a bigger resistance, which is 40.0 ohms. And then up here, I have a wire and a resistor. And this just goes back and connects here. And this resistance is 30.0 ohms as well. Your book, now this part is very optional. Like when I do make up a problem, for instance, I don't have to tell you any names for any currents. I don't have to tell you any directions. What you need to know is that it doesn't matter. Okay, you can call the currents anything you want, and you can say they're pointing any way you want. As long as you make up the equations consistent with them, then you'll still get the right answer. But because your book did it a very specific way, I'm going to show you exactly what currents they use. So they're calling that current going to the left I3. They're calling this current going this way and this way I1. And this current they're saying is going this way, and this is I2. They also went as far as to label this point right here A, and then this point B, this point C, this point D, this point H, and then they had a G over here, and they had a F over here, and they had an E over here. And the only reason why I'm writing all that is because it comes in handy when I go to specify what loop I'm doing and that sort of thing. So the two Kirchhoff's laws, one is Kirchhoff's loop rule, and it's basically a statement of conservation of energy. It says the sum of the voltage changes over any closed loop of a circuit. In other words, you start at one point in the circuit and you go all the way around and end up at the exact same spot you were. At that point, the sum of all the voltage changes will be equal to 0. That's Kirchhoff's voltage rule. With that, you've got to remember something. If you traverse or go across a resistor, the direction in the direction that the current is that you made up is flowing, then that voltage is a voltage. That voltage change is a voltage drop. If you go against the current, then the voltage change across that resistor is a voltage increase. So that's one caveat with Kirchhoff's voltage rule or loop rule. The other caveat is if you go across the battery from small arm to large arm, then you're going in a way that increases voltage. So that's a voltage increase. If you go from big arm to small arm, that's a voltage decrease. That one's pretty obvious, and most people don't have a problem with that, but they do forget the other one. So just remember, once you've chosen a direction for current, if you're going across the resistor, you've got to figure out what the change in voltage is across that resistor. And if that resistor that you're going across, if you're going across it in the direction of your current, then that's a voltage drop. If you're going the other way, then it's a voltage increase. Okay. And then Kirchhoff's junction rule says that the sum of all the currents entering a junction has to equal the sum of all the currents exiting the junction. Junction just means a point where two or more, or actually three or more wires come together. So we just want to keep that in mind, and that's the way we do it. So the first thing I'm going to do is I am going to write Kirchhoff's junction rule for, which we'll call KJR, or you could say KJL, Kirchhoff's junction law, Kirchhoff's junction rule, and I'm specifically going to do it for point A. So at A, what I see is a current I3 enters that little blue dot that I labeled A. So that's a current entering a junction. And then coming out of it is a current I1 and I2. So I'm going to say this is equal to I1 plus I2. And I'm going to call that equation 1. So that's the first, or one of the first steps. It doesn't really matter too much what order you do it in, but you always need basically one junction rule for every junction minus one. So this one actually has two junctions, A and D. If I made a second one, you'd find out that it's identical to the first. So it's always one extra junction than you need. Now let's look at going around in the top loop. So I'm going to actually go from, say, D to C to B to A, H, and back to D. So let's say top loop. And this is Kirchhoff's voltage rule, or Kirchhoff's loop rule is another one. That's another way you can do it. So I'm going to say the top loop. So I'm going to start at D, and I go to the left. Notice I'm jumping from a short leg of the battery to a long leg of the battery. So that's a voltage increase. So I'm going to say plus 45.0. I'm not going to put any units, but I should be thinking about them to make sure I don't make any mistakes. Now I'm going across a resistance of 1 ohm. Notice I'm going in the direction of current I3. So that's a voltage drop. But I'm also next going to go through a resistance of 40 ohms the same way. So in fact, I'm going to go ahead and combine those two and say this is 41.0 times I3. And now I'm going to hang a right because I've gotten to point A now, and I'm going up to the 30 ohm resistor. Notice I am again going in the direction of current. This time it's current I1. So since I'm going the direction of current, the resistor is a voltage drop. So I'm going to say minus 30.0 I1. And now I'm back to H and then to D, and I'll say that's equal to 0. That's going to be equation 2. Any questions on that? All right, I'm going to use the outer loop this time. Now, I could do just the bottom loop as well, but I'll show you in a second. Algebraically, it's kind of a smart move to go through the outer loop. So the outer loop goes basically from, let's say, from A to H to D to E to F to G, and then back to A. So now I'm going to say outer loop. And like I said, I'll start with A. And this is also helpful because when I get to that bottom leg, I'm going to be going the opposite direction of the current. So you can see what I meant about that little caveat. So I'm going to start at A. The first thing I run into is the 30 ohm resistor, and I'm going the direction of current. So I'm going to write that as 30.0 I1, and it's a minus in front of it because I'm going the direction of current. So that's a voltage decrease. Now I get to H to D, nothing happens. I'm then down on the 20 ohm resistor in the bottom leg, but notice I'm going in a counterclockwise fashion, which is the exact opposite direction of I2. So this one's going to be a voltage increase of 20.0 times I2. And actually, let's take that out. I'm going to make it even smarter because notice there's another resistor, a 1 ohm resistor. So I'm going to go ahead and combine that and say that's a 21.0 resistance times I2. Both of them, I was going the opposite direction of I2, so both of them were a voltage increase. Now I'm going from the long leg of the battery to the short leg of the battery. That means the battery is, in this case, a voltage drop. So I'm going to say now minus 80.0. And now I'm back to point A, so I'll say equals 0, and this is going to be equation 3. Now, if you'll notice, equation 2 and equation 3 both have I1 in it. So if I can find some way of making use of that, then breaking it up the way I did was a very smart move. So what I'm going to do is I'm going to solve for I2 in terms of I1 in equation 2. So let's say solve 2 for equation I3, or excuse me, for I3. So if I look at equation 2, I can pull the I3 term to the right-hand side. It'll become 41 I3 as a positive. So now I'm going to say I3 is equal to 45.0 minus 30.0 I1, all that divided by 41.0, and I'm going to call this 2 prime. Now I'm going to solve equation 3 for I2. Okay, the reason why I notice, since I have an I1 in equation 2 and equation 3, if I can solve for I3 in terms of I1 and for I2 in terms of I1, then I can put my I2 and I3 in equation 1, and I'll only have one unknown, specifically I1. That's the whole reason behind this. There's a bunch of different ways. You can even set them up where it's a coefficient times I1 plus or minus a coefficient times I2 plus or minus a coefficient times I3 equals just a pure number with no i's in it. Set each of the 3 equations that way, and then you can solve it using matrix techniques, Gauss-Jordan method, or reducing the matrix to 1 0 0 0 1 0 0 0 1. All those things are fair game. So when I do this with equation 3, I'm going to say I2. If I pull that one to the other side, it's going to actually be negative. So what I'm going to do instead is I'm going to pull the 80 volts to the other side. That's going to be 80.0. And then I'm going to pull the negative 30 I1 to the other side. That's going to be plus 30.0 I1. And then now all I have to do is divide it by my coefficient of I2, which is 21.0. All right. Now that seems kind of odd, but this will be called equation I3. And in fact, I can make equation 2 a little better by breaking that fraction up into numbers. So if I take 45 and divide it by 41, assuming I actually get to plug the keys in right, I get 1.098. So let's say I3 is equal to 1.098, which is more than enough sig figs clearly. 1.098. Then I'm going to say minus 30 over 41. So 30 divided by 41 gives me 0.7317. 0.7317 times I1. So this will be 2 double prime, say. And then I2, I'm going to call this 3 double prime. No, yeah, 3 double prime. And now I'm going to say 80 divided by 21. That gives me 3.810. And then 30 over 21. That gives me 1.429. And this is plus. And that's I1 there. Okay. And make sure my signs are right. I had a plus minus and then I had a plus plus. I got a plus minus and a plus plus. So that looks good. So now I'm going to plug 2 double prime and 3 double prime into 1, specifically because I will then have only the unknown I1. So I have I3, which is on the left-hand side, is equal to 1.098 minus 0.7317 I1 is equal to I1 plus I2, which is 3.810 plus 1.429 I1. So now you can see I can get all the stuff of the I1s together. So the right-hand side right now is 2.429. So I'm going to change it to the left side. I'm going to say that's 2.42, whoa, 429. That's just from adding the I1 and this I1. Now I'm going to pull this 0.7317 over. That's going to become plus as well. So I say plus 0.7317. All that times I1 is equal to, so now I've taken care of this other guy as well. Now I need 1.098, and I'm going to pull that 3.810 to the other side. That's going to become minus. So 1.098 minus 3.81 gives me 7.288. That's not right at all. Oh, no wonder I typed in 11. Ooh, that's so dangerous. Okay, so I'm going to take the 1.098 minus 3.81. Dang it, I just hit a bunch of buttons at once. Now I got to do it again. 1.098 minus 3.81. That gives me negative 2. Well, negative 2.1, or excuse me, 2.712. So now I can see that I1 is going to be negative 2.712 divided by 2.429 plus 0.7317. 2.429 plus 0.7317. That gives me negative 0.8580 amps. That's one extra sig fig. Now notice that's negative. All that means is that we chose the wrong direction for I1. I1 technically should be going instead of up and to the right, it should actually be going to the left and then down on the left and up on the right. But now that we've got all those equations in terms of that direction, we just have to keep sticking in the negative value whenever we need I1. But that being said, we now have the current I1, which is helpful. Okay. And in fact, if I look, your book came up with negative 0.87 amps using the exact same numbers I did. In other words, I actually took their example instead of just made up my own like I normally do. So now that I have I1, remember we were wise enough to solve for I3 in terms of I1 and for I2 in terms of I1. So now I can just plug that in. I'm going to say I2 is equal to 3.810 plus 1.429 times I1, which we got was negative 0.8580 amps. Yeah, good enough. Okay. So I'm going to say that negative 0.8580, I'm going to multiply that by 1.429. And then I'm going to add to that 3.8107. And that gives me 2.58. And the last one is a 4 that rounds to a 5. So I'm going to write 4.5 on that. And that's amps. And that one's actually positive, but that is I2. Now, for your book, it got I2 was 2.6. So that's pretty close. I got 2.58. They got 2.6. And now I can use I3 as well. I3 from 3 double prime is in fact equal to, no, I3 from 2 double prime is in fact equal to 1.098 minus 0.7317 times I1, which is negative 0.8580 amps. So I'm going to take negative 0.8580 times negative 0.7317. That gives me ultimately a positive. And now I add that to 1.098 plus 1.098. And that gives me 1.726 amps is equal to I3. I'll circle that as well. And when I look, it said 1.7 was I3. So I got all the right answers according to the book example anyways. So any questions on that? Your book has a whole table describing how to implement the Kirchhoff rules, but that's basically it. The only part that's really messes students up is one, they're usually a little scared to just write which direction the currents are going. So if you were actually not solving a multiple choice type problem, that would be a problem, for instance, in homework and stuff like that. But when we're doing the actual test, they are going to usually be drawn because they're specifically asking for a specific current, and they can't do that unless they give you the direction and the label, because otherwise the negative value wouldn't mean anything because you don't know which direction they were choosing. So you're lucky in that you're doing multiple choice questions, so they'll normally supply them, but you don't have to. And just remember, if it comes out negative, you got to continue using it negative. That just means it's the wrong direction. So that's one of the problems, is students being sort of hemmed in or worried about handcuffed, if you will, by not knowing exactly which direction each current goes. But that doesn't matter at all. You just take a guess You take 0 time on it, take a guess which way it's going, work all the equations accordingly, and it'll work out. The other thing, like I said, is when you cross a resistor, that's going to be a voltage change. And normally you think resistance is a voltage drop, but if you're going the opposite direction of current, then you're literally saying the voltage is an increase. So you have to use that. If you go the opposite direction of current, the resistor is a voltage increase. If you go the direction of the current, a resistor results in a resistance decrease, which is, again, from Ohm's law, V equals IR. So there's plenty of examples for you to use on this. I definitely recommend you try to look when you're writing the equations, choosing which loop you go around. Look for the 2 equations to have at least one of the same currents in both of them. Then you can always use this technique that I just did, which was solve one of the equations in terms of the one they have in common, and then the other equation in terms of the one they have in common, and then you can stick them all in the junction rule. All right, now that we've done that, I've basically covered how to do circuits. So you should do as many of these as possible, but really the last thing that's of importance from this chapter is you should be able to apply the more or less blindly the actual equations that they get by solving the Kirchhoff loop rule in differential equation form. So normally I take the time to derive all that. You can see that in my videos on my YouTube channel, but I'm just going to give you the results right now. If you're charging a capacitor, okay, you might have a circuit like this, for instance. So let's take a battery like this. And let's say this battery is going to run up. It's going to go into a resistor R. And let's say this voltage, or this battery, has a voltage of E, that script E there. So it's like an EMF. And that R can represent the total resistance of the wire plus the resistance of any resistors you have in there. That's fine. And that should be the way you do it. Now you go over here and the battery is, or the wire is going to run into a capacitor, and that capacitor is going to have a capacitance C. Now, the big part is they're going to have a switch here that allows you to throw it. And when that switch is thrown, what's going to happen is the positive side of the battery, which is the top part, and the negative side of the battery is the bottom part. But that top part is going to compel charges of a positive variety to run away from it. So you're going to get a flow of positive charges around the bend. Remember, that's conventional current too. It's the direction that positive charges go. So it's also saying that. Now, what's going to happen is you're slowly going to build up positive charges on here. But as each charge gets on this plate, on the top plate, the bottom plate is going to answer by having a negative charge, and then another, and then another, and then another, until the voltage across that capacitor is equal to the voltage of the battery. At that point, no more current will run, and there will be 0 voltage drop across the resistor. It's going to be acting like it's just a circuit with a battery and a capacitor. So that's physically what we know happens. The Kirchhoff's junction rule for this turns out to be E minus R I, which is IR, and that's dq dt. Remember, current is dq dt. And then we have minus 1 over C times Q equals 0. That is Kirchhoff's loop rule for this particular circuit. When we solve that differential equation, it's actually very straightforward. It's not a hard differential equation. We end up getting the following solutions. The Q is equal to the capacitance times the voltage of the battery times 1 minus e to the negative t over RC, which can also be written, which can also be written as Q0 in some sense, meaning the maximum Q it could have, times 1 minus e to the negative t over tau, where tau is called the time constant. and it literally is just R times C. Okay. Now, remember, V is given by Q over C. So you also get V is equal to, if I take this Q that I have and divide it by C, then I'm just going to get this E times 1 minus E to the negative T over tau. So that's the equation for the charge. You can see it's basically 1 minus exponential decay, which means basically you have an asymptote at CE in the case of Q. You have an asymptote at Q at CE that it's going to approach over time. Similarly, the voltage is asymptotically approaching a voltage of E over time. Now, the other part that's kind of weird is you actually need the current too, and I is dq dt. So you could actually take the derivative of Q with respect to time, and you would actually get E over R times E to the negative T over RC. So what happens here is exactly sort of the opposite, if you will, of what we had for the voltage and the charge. In the case of the current starts off like, really big, because it thinks there's the voltage difference of E volts. So it's going to start out with a really large current, but that current's going to decay over time. And that's what we're seeing with that equation. In fact, if you look at a graph, say, of Q/V as a function of time, what you're going to see is, let's do blue. I will do Q with blue. So actually, let me do it this way. So I want to plot Q in blue, and Q has a quantity C times Z that it will ultimately meet. Notice that quantity is literally the capacitance times the voltage of the battery, and that's exactly what you'd expect to be the voltage across the capacitor if that's the only thing in the circuit with the resistor. In this case, it's actually going to start it at T equals 0 like this, and it's going to go up, 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 up like that. And in fact, if you look at it, E to the negative 1 is actually equal to 36.8%, basically, or about 37%. So what you get is, after one time constant, which is tau equals RC, it should be about 0.63 times CE. If you wanted to do the voltage, then the voltage might be something like this, and this would be its asymptote, and it would go off and approach that like that, and in fact this would be 0.63 E. So that's really what the current or the charge and the voltage are doing. Whereas the actual current, if we tried to plot that one, let's use a black graph for this. The actual lines will be black. This is T and this is I. So it's going to start off at a nice quantity of E over R, because T being 0 gives you E to the 0, and E to the 0, or anything to the 0 power other than 0, is 1. So we're just starting off with that, but now it's going to exponentially decay like this, so that in fact at tau equals RC, this will be 0.37 E over R. So really, you're completely free to use these equations. You should have them on your equation sheet. And when you have a problem, it'll say something like the capacitance in a circuit is C equals 0.30 microfarads, and the total resistance is R equal 20 kilo ohms, and the battery has an EMF of 12 volts. Determine the time constant. Okay, well, that just means take my 0.30 microfarads and multiply it by, since we're actually wanting the RC, we have to take that capacitance and multiply it by the resistance, which was 20 kilo ohms, and a kilo times a micro gives you a milli, excuse me. So we'd end up getting basically 6 milliseconds is the time constant for that case. So for, let's write this as an example. R equals 20 kilo ohms and C equals 0.30 microfarads implies tau equals RC is equal to 6.0 milliseconds. That's just from multiplying those two. Then they say, what's the maximum charge the capacitor would acquire? Well, the maximum charge a capacitor could acquire, Q max, is really that asymptotic value, which is C times E. That's going to be 0.30 microfarads times 12.0 volts. If we were actually using, it was using 12 volts. So 12, well, if you did 12 times 3, you get 36. So 12 times 0.3 is 3.6. So this is going to be 3.6 micro coulombs. They ask, what is the time it takes to reach 99% of the value of that value? So that was part A. This is part B. Part C, T equals question mark when Q equals 0.99 CE. Well, all that means is you're going to write 0.99 CE is equal to CE times 1 minus E to the negative T over tau. So you can see that the CEs cancel out and you basically get 1 minus 0.99 is equal to E to the negative T over tau. That means 0.010 is equal to E to the negative T over tau. I'm going to take the ln of both sides. And that's going to give me the ln of 0.01. That gives me negative 4.605. Is equal to, now the natural log of E to the negative T over tau is just negative T over tau. So T is actually equal to positive 4.605 times 6.0 milliseconds, which gives me 27.6 milliseconds. So the time constant is in fact 6 milliseconds, and it's going to take about 4.6 of those to get to 99%. That's really what you're going to do over and over and over again. If you want the maximum current, that's what part D is asking for, or E is asking for. D, the current, I, when the charge is half its value. So that's just another case where you're going to solve for the current at a particular time, but you first got to use the Q to figure out what time that is. So this is really all you're doing with these capacitor problems. And you can see the examples are pretty straightforward. You can also look in my YouTube channel. You can see various examples. Now I'm going to remind you that that was charging a capacitor. Okay. Now we're going to do discharging a cap. Another word for capacitor, by the way, is a condenser. But in this case, you've got basically I times R minus Q over C is equal to 0. That's Kirchhoff's loop rule. And of course, I in this case is actually going to be negative dq dt because I goes up as the charge on the capacitor goes down. Now, when you go through that process, you get these answers. You're going to get Q is equal to the initial charge of the capacitor times e to the negative t over tau. So that's another equation you're allowed to use. V is going to, and this is technically V across capacitor, is going to be the initial voltage across the capacitor times e to the negative t over tau. Same tau though, so it's still tau is RC. And then the current is actually going to be exponential decay as well. And we'll get I. This is basically from taking the negative derivative of Q with respect to time. So I turns out to be Q0 over RC times e to the negative t over tau. Johnny, can you call my mom and let her know I'm busy, baby? All right, so that's the equations that you're going to use for discharging a capacitor. And that's really the last thing I wanted to cover, is just so you know how that works. You'll see example 2611 for this one. And see example 2610 for this one. So that's all you really need to do. And I'm not requiring you to do any derivations. You just need to know what all those symbols are so that you can plug them in. And then you need to know how to solve for instance, either the argument of a logarithm or the exponent of something, raised to a power. So that's the only complexity of it. Any questions on those two? No question. All right. So this is supposed to be fairly easy. I've already went through and picked out the more complicated stuff. If you see anything where you're solving for a circuit, well, actually, you should get plenty of practice with it from the practice midterm. You can, or excuse me, the practice final, and you can also do just chapter 26 in the review section where I just got chapter quizzes. You can do chapter 26 till the cows come home and get plenty of experience on the type of problems that you want. And those are never even checked, but the practice test, the practice final exam, you do want to do, because that's part of your extra credit, where I take the sum of all your highest practice test grades, divide them by the number of practice tests, and then divide that answer, that average, by 20, which means you can get up to 5 points added to your course grade. Okay, so you definitely want to do that. I'm going to leave this for a second, and we're going to now go to, in fact, chapter 27. This is why I think I can actually get 27 and maybe even 28, because I'm skipping the the safety stuff and all those things are just things you should read. I did decide not to make ammeters and voltmeters out of galvanometers. That's another section in your textbook. I might have missed a few in the test bank. So if you see those, just know that's not going to come up. If it says use the galvanometer that has such and such a deflection with such and such a resist or such and such a current, just know that's a problem that I'm not expecting you to do. So don't worry too much about that. And then it goes how to connect meters and effects of meter resistance and other meters and stuff like that. Those are all really important things that you should read, especially if you're considering EE or electrical engineering. Then those are worthwhile. Mechanical engineering too, you sort of need a little bit of electricity and magnetism. But what I'm more concerned about is just your ability to solve DC circuits like the one I just did, and to apply this charging of a capacitor and discharging of a capacitor formula, which I think is really, really easy. Now, that brings us to chapter 27. Anybody have any questions on that before I jump to chapter 27? Because I'm not going to do much in it, but I am going to do some. We only got like 12 minutes, so I can't do much, obviously. Okay, so the first thing I want to tell you about chapter 27 is, and I think you might have done something like the Faraday lab with Mr. Mitchell, but basically if you imagine this pencil is a current carrying wire. Okay. So this pencil, if it was a current carrying wire, let's say the point points in the direction of current. If I were to grab this with my right hand like this, where my thumb points in the direction of the current, then I look down like that, and my fingers are wrapping around that current in the same direction the magnetic field is. So what that means is if this current is going out towards you, when I put my right hand around it, that means right here, the magnetic field is this way. Right here, it's this way. Right here, it's this way. And right here, it's this way. And then in between those, of course, it's like a 45-degree angle, 45-degree angle, 45-degree. That's the key point to understand, is a current carrying wire creates a magnetic field, and that magnetic field is concentrically around it in one way or the other, as given by the right hand rule, where your thumb's pointing in the direction of the current and your fingers are curling around, again, only using your right hand, in the direction of magnetic field. Okay, so when I say something like that, that means, for instance, like I said, this wire right here, you're looking at the end of it, current's coming to you. And since the current is coming to you, right here, directly above, the magnetic field points that way. And right here to the, what I call your left of it, and I think that's what y'all are seeing, it's going down. Below it, it's going that way. And to what you say is your right should be going up. So that's a right-hand rule. You got to know it. You got to use it over and over. It turns out, though, that the magnetic field is a weird little monster. Okay, it's a weird little monster in that, one, we use a compass to find the magnetic field of, or excuse me, the north direction from a compass. What's weird, though, is you can make a compass. You can take just a sewing needle, for instance, and rub it or bring it by a magnet several times like this. And since it's made of steel, it will automatically start to become ferromagnetic, or it's, basically it's already ferrous material. It's already iron. And by exposing it to a magnetic field, it's going to match that magnetic field, and you'll get one end will be the north pole of the magnet, and the other end is the south pole of the magnet. And you can take and glue that to like a little short cork, or maybe a round piece of cork that's sort of cylindrical and very thin. You glue that to that piece of cork, and then stick that piece of cork on water, like in a cup or something. And then that wire, or excuse me, that needle will align itself to point towards the north magnetic pole of the Earth. That tells you something that you might not have realized, but the north magnetic pole of the Earth is actually a south pole. Okay, so we actually picture the Earth as this globe, and it's got a rotation axis that's tilted, but then tilted with respect to that is a bar magnet. And the south end of that bar magnet is, in fact, very close to the surface up in northeastern Canada. So there's a big body of water, and roughly that's where the magnetic north of the Earth is, even though it's technically a south pole. Okay, which brings me to another thing. I use this mnemonic because it normally makes people remember it, and specifically the mnemonic is magnetic fields are sort of like old people. They leave the north and enter the south. So if you have like a magnet, and let's say this is the North Pole and this is the South Pole of the bar magnet, then the magnetic field lines point out of the north, curl back around, and come in the south. And in fact, they continue through the magnet. Unlike electric fields that didn't continue through, for instance, metals, the magnetic field always makes a complete loop. Okay, so you need to know that. You need that the North Pole has actual electric field lines leaving it, and the South Pole of the magnet has actually magnetic field lines entering it. You also need to know that the north magnetic pole of the Earth is, in fact, a south magnetic pole. And you should know, of course, that it's not at the actual north pole of the Earth, which is aligned with our rotation axis. It's off quite a bit, and it moves constantly. And in fact, we know from the fossil record of stones and various things that over time, on the order of hundreds of thousands of years, the Earth's magnetic field flips back and forth, back and forth. So like right now, we have the South Pole of the magnet is up near Canada and the North Pole is down in the Southern Hemisphere. In the next, let's say somewhere between 200 and 500,000 years from now, we're probably going to be in a spot where the South Pole of the magnets down in the Southern Hemisphere and the North Pole of the magnets in the Northern Hemisphere. So that just comes back and forth. We don't really know why, and we also don't know exactly all the details of why the Earth has a magnetic field. We do know that planets that are comparable in size to Earth have a molten liquid part of their core. It's an outer core for our planet. And when we have a molten core, that means a lot of the atoms are ionized. And if the planet is rotating, we know that charged particles accelerating creates electromagnetic radiation. So we sort of think there's like something we just call a dynamo effect, which is really just giving a name to something we don't understand. But we think that's the cause of the Earth's magnetic field. And the data that we have that is consistent with that, for instance, is Venus is about 98% of the size of the Earth. So we expect its core to be exactly as hot as the Earth. It's roughly in the same area of the solar system. So we expect it to be made of nickel and iron in the core, just like the Earth is. But Venus has almost no magnetic field. And what we do know about Venus is that it's this weird planet that rotates and revolves like most planets do, but this one actually rotates in the opposite direction it revolves. We think that's because in the early formation of the solar system, something really big, maybe something the size of the moon, or maybe even as big as Mars, hit Venus and caused it to rotate in the opposite direction. And it actually rotates so slow that a day on Venus is longer than a year. Remember, a day is the time required for the planet to make essentially a 360-degree rotation, whereas a revolution is a year, and that's the time required for the planet to go from this side of the sun back to the side again. So the literal day of Venus is longer than a year, but that's because it goes so slow and it's going backwards, and therefore that's some data suggests there are ideas about the magnetic field needing a molten core and a rotation speed is consistent with our understandings. Okay, so that's some stuff to know. The other things to know, for instance, is let's draw. I'm going to go ahead and share my screen once more because we only got about 4 minutes left, and it probably take that long just to pull it up. So I'm going to draw these results, and I'm going to give you some equations that will come in handy. So first off, if I drew the Earth, it would be essentially a sphere like that, roughly. It'll come up in a second. It just takes a little while. There it is. Okay, so what we know is the Earth's rotation axis. Whoa, no. The Earth's rotation axis is tilted about 23.5 degrees. And then inside of this, we can sort of picture a bar magnet like this, with the South Pole up here and the North Pole down here. And in fact, this would be our equator. That's the worst word equator ever drawn. And this is the North Pole. And this is the South Pole. Okay, and as I said about magnets, magnetic fields are like old people. They leave the north and enter the south. So that's something you need to know. Okay. Bar magnets, of course, or excuse me, horseshoe magnets, of course, are sort of similar. They have a North Pole and a South Pole. And by the way, if you ever cut one in half, you don't get a North Pole and a South Pole separately. They just make two new magnets until you do it so small that they can't. So in this case, we're going to say the magnetic field lines come out of here and go into here.
Professor,
Yes.
isn't the magnetic field going the opposite way from the south to north?
Uh,
I don't. Maybe I'm just wrong, but I took an astronomy, like intro astronomy class, and like that was the one thing our professor was like, you need to take this away from the class, and I could probably just be remembering it wrong.
yeah. Well, if you look at it, basically, you know, the North Pole of a compass points towards the North Pole,
Mhm.
the North magnetic pole of the Earth. So that tells you it has to be a South Pole. And if you look at the figures in our book, it's got similar sort of things. So yeah, that's the way that works.
Yeah.
And the field
That makes
lines are weird.
I got you.
Okay. So now the things that you need to be able to do is in the algebra-based physics class, we say F equals Bill. And we really have to put a sine theta on it because really it's only the component of L perpendicular to B that matters. So if you're talking about a wire immersed in a magnetic field, it feels a force given by the current times the length of the wire times the strength of the magnetic field times the sine of the angle between L. So if this is your wire, for instance, and your current's going that way, then L can be seen as a vector that points parallel to the current. And let's say the magnetic field could be this. And when they're tail to tail, that's the angle theta. Okay. The magnetic field has a unit of the Tesla, named after Nikola Tesla. But another unit we use is the Gauss, which is about 1/10,000th of a Tesla. The Earth's magnetic field is around a half a Gauss, if I remember correctly. You can double check me on that, so I'll just say check.
Professor.
Yes.
So I just Google it. Looks like the Earth's magnetic field on the outside. On the surface, like outside above the Earth's surface is from N to S. So should from S pole to N pole.
Yes.
Inside the Earth is from S to N.
Oh, okay. Well, I would just say whatever you're looking at might have an error there. If you, for instance, look at figure 27.5, I'll do that for you guys. See figure 27-5. That actually shows it to you. So check that out. You'll see that it does draw a bar magnet tilted. It has the south near the north, and the field lines are coming out of the north end of the magnet and entering the south end. So my memory seems to be correct with all I've learned from physics, but like I said, there might be some misunderstandings. A lot of people don't take the time to explain to people that the compass north end pointing to the north means the south end has to be south. So a lot of people just don't know that. The other thing is if you're getting a little bit more fancy, and we're going to do some problems with this, then there's a differential force, which is equal to I times dl cross b. So that's a whole nother integral. I'm going to solve two problems like that next time, and then I'm going to show you Ampere's law and the law of Biot-Savart. But you can look at that now and see, for instance, how they do calculate the force on a current carrying wire. For instance, in your book, it has one where there's a wire going up carrying a current, and then it goes over a half circle and then goes continuing down, and you can calculate the total force on it using that integral equation. So I just wanted to give you that so you can get started on stuff. You're probably not going to be able to do those integrals yet, but you can definitely look at the integrals on my YouTube channel to see how it's done, and I will give it to you next time. So we are done. If anybody wants to stay late, has any questions, feel free to. Everybody that came in late or maybe wasn't listening at the right time, I did send an email out to all of you to your TCC account about the test and the chapters that are covered, but the practice test is now up and it goes all the way through 28. And on Wednesday, I'll let you know whether 28 and 27 will be on there. So far, I'm thinking at least 27 is going to be on there. Okay. So you're free to go. Thanks for coming, everybody. Anything else?
Thanks, Professor.
You're welcome. Trying to think if there's something I'm supposed to tell you. I can't remember it. All right. Have a good one. I'm going to talk to Mr. Mitchell and find out about him proctoring the test or whatever. So I'll let you know when I know. Thanks, Bohan and Jong and all you guys for contributing. I appreciate it. Guys. But
Professor.
Yeah, Bohan.
So I look at just for the direction. I just check the textbook. It's still saying the same thing. Looks like the magnetic field from the North Pole, which is which should be the south on the Earth,
right?
And to the South Pole, which is north of the Earth. That's like outside. That's like above the surface of the Earth, but the inside is from South Pole to N Pole.
Are you seeing the figure that I just posted up and shared?
Oh yeah, I saw this picture as well.
Okay, so you do see the South Pole of the magnet is near Canada.
Right.
And you see that the lines are actually coming out of the north end. That's what that little arrow right there means. And then it loops back. So that's probably what you're referring to. Is this out here?
Right.
Yeah, they're going from the south to the north. Yeah, that's an important thing. So
right.
Yeah, I think we're both talking about the same thing, but you're making well, you're actually making good sense because it tells you that this field is pointing towards the north on the outside of the Earth, which is really what we wanted.
Right. And I also look at it, said that it's so for the magnetic things, so that is the field line like above the surface of the Earth. Right. But if you look at inside, it should be good from source to the north.
Oh, gotcha. Yeah. Well, if you're talking about below the surface of the Earth, yeah, absolutely. It's going to look a little weird. It'll actually, as you can tell, like right here, it literally is pointing the opposite direction as it is right here. So this is pointing northward. If we go inside the Earth right here, it's literally pointing southward and underground. And in fact, there's a thing called the magnetic declination. And that's really the fact that the magnetic field is not parallel to the ground. It actually dips below horizontal, and that's called the magnetic declination. So that's something else.
Also, I did the homework for chapter 27 last weekend already. The few questions that I was just kind of lost. Can you please look at it?
Yes.
So I got a homework question number 5.
Okay, you want to share your screen?
I can. I mean, it just. I use a different device. It's not on my.
Okay, so it's not on the computer. Yeah. Gotcha.
No.
And you're seeing homework 5 or problem 5 from chapter 27?
Right.
I'm going to see if I have access to that right now, and I'll pull it up. So instructor tools, assignments, and this is the homework, not the concepts, right?
No.
Oh, it is the concepts?
No, it's not. It is a homework.
Okay, gotcha. So homework, chapter 26, or excuse me, 27, right?
Yes.
And then number 5, torque on a current loop in a magnetic field.
Yes.
Now let me do a share screen again. So you're all talking about the same thing. Looks like it's going to be this one. So this is the problem you're talking about?
Yeah, that is the problem I was talking about.
Okay, so it says to understand the origin of the torque on a current loop due to the magnetic forces on the current carrying wires. That's your learning goal. This problem will show you how to calculate the torque on a magnetic dipole in a uniform magnetic field. We start with a rectangular current loop, the shape of which allows us to calculate the Lorentz forces explicitly Then we generalize our result. Even if you already know the general formulas to solve this problem, you might find it instructive. So what they're looking at right here is this diagram where you have a current going this way, this way, this way, this way. What I tell my students, one of the ways you can do a cross product is use your fingers like this, where your index finger points straight ahead, your middle finger is pointing at a 90-degree angle from that, and then your thumb is a 90-degree angle to both of them. So I times DL, current should go the same direction as the DL vector. So that should be this way. And then your B would be this way. And then this is your force. So if I look at that top current in the loop, that appears to be coming out of the page. So I times L is this way. The magnetic field appears to be going to the right, which is where my finger is right now. So that's good. So it suggests that that top wire is actually going to have a force in the upward direction. And then that bottom wire is going to have a force in the downward direction. And they're basically going to essentially cancel out. But if you look at the left wire, then you have the QV going that way. And this tends to rotate it out or have a force out of the page. And the back one has a force in the page. So that's how that works. Is there a more specific question you have, or did I cover talk about that?
So you said the top wire and the bottom wire canceled out.
Well, in principle, they all do by forces, but torque is what matters when you're calculating. What you have here is a loop of current. A loop of current is a form of what we call a magnetic dipole, just like we did an electric dipole.
Okay, so when we look at the torque, we don't really consider the single wire. We just look at my surface.
Yeah, well, you can assume, for instance, the magnetic dipole has a direction that's perpendicular to the surface that the wire is in, but you can still take the individual wires and treat it as if that's either a current or positive charges moving in the same direction as the current, and wire by wire figure out what the forces are. But if you just think about forces, you'll get a net force of 0. But if you think about torques, you'll actually have a torque, which is a force times lever arm for each end, and two of the forces are actually helping each other rotate.
Yeah, when I look at the formula, it was like as I believe the torque is NBAI sine theta. So the A is the area, the normal force of the area, which is a vector. So that's why like it kind of makes sense when I just look at my surface as a whole surface. But I don't know, like I did the same thing as you explaining beginning. I just tried to look at as each single wire, but I just couldn't figure out by that way.
Okay, what I would do is look at where your book derives it in chapter 27. I think it is either chapter 27 or 28. They take the time to derive a magnetic field, but I think it is in 27. That'll make a little bit more sense to you. But what we ultimately conclude is that just like having a positive charge and a negative charge that are identical in magnitude but separated by some distance, we can represent that as an electric dipole by a vector that points from the negative charge towards the positive charge, and the magnitude of it is the distance times the charge, the magnitude of the charge. That's the electric dipole. When we do that, we get torque is equal to P, the dipole, cross with the electric field. When we do the same thing for current, it turns out that the dipole will be basically the current around the loop times the number of loops. So if you have N loops, it's going to be N times I times the area, which is pi squared, for instance, for a circle. And that's the magnetic dipole moment. That is a mu, and the torque is mu cross B. So instead of P cross E, which is what we had for electric dipole, we have a mu cross B as in boy for magnetic dipole.
Okay, I think I saw that formula.
Yeah, I think this formula, this
the mu is equal to NAI something.
Yeah, NIA or NAI, yep. And they use a vector symbol. where if you wrap your right fingers of your hand around the dipole in the direction the current's going, then your thumb points in the direction of the dipole. So the vector, treating it as a vector, is perpendicular to that plane.
Okay. And I also had the question on the number A. So number A, the part B, I just don't know how do you calculate the P? Like
Oh,
this?
number 8, you say?
Yes, number A.
Let's pull that up. Okay, so I've got that up now. And what they're doing is determine the radius R and pitch P. Oh, okay, gotcha. So the pitch P, which is the distance between the loops. So the vectors of velocity has a component that's parallel to the magnetic field, and that does nothing, is not affected by the magnetic field at all. But the one that's perpendicular to the magnetic field, that carries a force, and that's what makes it go in a circle. So once you find the frequency of the whatever the charged particle is to go from here at the top of the helix, one complete loop to the top again, that's the period.
Okay.
So
But it's
take that period and multiply it by the velocity parallel to the magnetic field, and that's the distance between two consecutive loops.
So you get you use your V times the period, like how many times for a circle, and
just the velocity, the component of velocity that's parallel to the magnetic field. You just want to multiply that by the period. And remember, we learned a way to solve for the, or you learned a way to solve for the period in chapter 27, which is basically mv squared over r. That's the MA part of F equals MA, has got to equal Q times V times B. So Q,
yeah, I think I remember that, but so I find out this the solution from online, but it had something that said cosine theta, which I don't understand. What's the cosine theta talking about?
So remember the sign, when you have two vectors tail to tail, the sign, the component of the vector perpendicular to the other vector. So for instance,
okay, so we only talk about the horizontal vector of the.
Yeah, exactly. So the sign gives you this component, which is perpendicular to this vector. Cosine gives you the one that's parallel to the magnetic field. So that's why they said cosine.
Okay, I think I got it now. So we use the horizontal, the vertical, the horizontal vector of the V times like how many seconds you use you run for one circle, right?
Exactly. That's how long it gets to drift parallel to the magnetic field. So if you multiply that time by the velocity parallel to the magnetic field, you get the spacing between the loops.
So for this kind of motion, because it's one circle, it cannot be from the same point to the exactly same point. It just kind of like from like the 90-degree the top to the 90 degree. Okay.
Yeah, you have to imagine it sort of like pretending there's no dimension parallel to the B, and then it would be exactly it. Or you could just think of maybe it's casting a shadow on the new spot.
Yeah, I was just wondering how you can think about like those like a pair time stuff. Like, okay, now I see. Thank you.
No problem.
Professor Younger, I had just a few things about the final. I just want to make sure that I'm on the right page. So you said the chapter, anything, all the homework that, so we're only doing the homework till 26 or 28? Like,
yeah, 27 and 28, I'm going to count as extra credit. I might even do something that I normally don't do for extra credit and make it even worth more. But the main thing is you can get plenty of practice with 27 and 28 by doing the practice final. That's
so like everything. Oh, I'm sorry. Sorry. So everything like 27A, 27, 28, or 30, they all count as extra credit now?
Yes.
Okay, great. And one thing that the Professor Metro, he was just asking, he wants us to get a confirm from you that so the final is gonna be on Monday.
Definitely Monday. I got to talk to him about whether he can administer it, because I don't know if he's going. He had a vacation or something he was planning. He might not be there. So I might have to do it, or I might just let you guys take it on Respondus.
Okay, that sounds fair enough.
Okay.
If we're doing the like lockdown browser whatever, you will give us actually a time frame, like or just any time that day you pick what time you want.
Oh, okay. So what it's supposed to be is 2:30, because I think that's the time your lab normally starts. It's supposed to be 2:30 on Monday.
Okay. All right.
Okay. If worse comes to worse, we could even do it and I could observe it over Zoom and we do it at 5:30. But so far we're shooting for 2:30 on Monday.
Okay. One last thing. When it's the what they call the final practice can actually release the final practice.
Oh yeah, I put that up today. It just
today.
just before class started.
Cool. Thank
And
you.
the last two questions are from chapters 27 and 28. I'm now almost certain we're going to have 27. Essentially certain we're going to have 27. But the last two questions are 27 and 28. So if you don't think we're going to do 28, you can just stop doing those.
Yeah, I was working on the chapter 27 question, and some of them kind of easy, but some of them are like really hard. Like,
yeah, the fact that you're getting through it at all without me covering it's pretty good. So you're understanding better than most people do. So don't worry about it. Hopefully we'll cover it better in the next couple of days.
All right, thank you, Professor Younger.
All right, have a good one. Bye.
Thank you too. Bye.
Bye-bye. Zhang, are you still here?
Yes, I'm still here.
Do you have a question, sir?
Yes. Could we do you still have the notes pulled up by any chance? Like I think it was like the first schematic that you drew out
Yeah, I can pull
that
it up.
we kind of redid. Yeah, sorry, I just had a quick little question on it.
No problem.
And also, while we're on the sorry, go ahead.
Do you think it was the first schematic I drew?
Yes, it's the one that we kind of reworked.
Okay.
But while we were on the topic of the like the homework and stuff, so I was behind on the homework, but just to clarify, the conceptual you don't take as late work, or you don't take late homework at all.
I take any of the late stuff. It's supposed to be up to 7 days late, but I think I've got it set where it'll take it. It's just going to take out a maximum number of points once you're 7 days late. So by all means, if you got any that aren't done, do it. And then as you do them, let me know so I can see that the grade gets changed.
Okay, got it. Sounds good.
Right.
So right here,
Yeah.
the resistance of the EQ, EQ1 was 222.2 ohms.
Right.
And the next one, right down there, like you boxed it, it's 522. I might have missed
Yeah, it was 522.2 because I made a calculation error.
Right. And how did we get from, so where did that number come from? I might have missed that little detail.
2000 divided by 9. I had actually evidently hit 8 by mistake and it gave me 250 and I took it like a dummy. But it would have given me 222.2.
Right.
Now that's this resistance right here is 222.2, which is in series with 300. So that's 5.
That's right.
2.
Oh, okay, great. That's right. You just added them. Okay.
All right. Thanks.
Because I was looking at it and I was like, wait, hold on. Where did that 550 come from?
Yeah, it wasn't that clear, and me making one arithmetic mistake and not finding it for that long made it really a nightmare.
That's okay, no worries. Okay, well, sounds good. And I mean, the final exam and everything was clarified, so appreciate that.
Have a good one, John.
All right, you too. Thank you so much. Have a good evening.
Bye-bye.